Today we are going to be looking at the first part of bioeffect and safety in ultrasound. Before we begin, I want to appreciate these wonderful people who have contributed greatly to my knowledge. So, what do you mean by the term bioeffect in ultrasound? The term bioeffect in ultrasound means that a biological effect or an adverse effect on biological tissue that occurs due to exposure to ultrasound. In general, we believe that ultrasound presents no risk to the patient or the operator. Now, this is because ultrasound is a form of non-ionizing radiation, unlike X-ray, which is a form of ionizing radiation. Also, so far, no proven adverse effect has been reported at the level of ultrasound practice. But however, ultrasound is a form of mechanical energy, and this energy, when passes through human tissue, most of this is converted into heat energy. It has the potential to produce biological effect. The ultrasound should be used in a prudent manner because of this, to provide medical benefits to the patient. The ALARA principle should be employed to avoid or prevent risk of bioeffect, and I'm going to tell you what ALARA principle is in a moment. So how could high frequency ultrasound wave cause bioeffect? Now, you have to understand that sound is a mechanical vibration of particles or molecules of a medium. So when a transducer is applied to biological tissue, there is this cyclic vibration or displacement of particle in the medium that occurs. The propagation of sound also produces localized forces and stresses in the tissue that are related to the change in the pressure, density, and temperature of the medium. Now, the strength with which the particle of a medium vibrates is determined by the amplitude of the wave and will depend on the power and intensity of the ultrasound beam, in other words, the ultrasonic field. The rate at which this particle will vibrate is determined primarily by the frequency of the transducer. Ultrasound waves of sufficient intensity transmitted in biological tissue can adversely affect and damage biological tissue, and this is well documented in experimental studies on cells in culture in vitro studies. Now, and also on living plants and animals in vivo studies. However, numerous epidemiological studies have been done over time for evidence of biological effect in patient population, and to date, none have shown any conclusive evidence of adverse effect from clinical use of diagnostic ultrasound in humans. So what determines the possibility for biological effect? There are acoustic output quantities to consider. Number one is pressure, two is power, and the third one is intensity. Let's look at pressure. Pressure is the amount of force applied over a given area. The unit of pressure is Newton over meter square, or Pascal, or millimeter mercury or atmosphere. Now, when a transducer emits ultrasound waves, the waves propagate in tissue by virtue of molecule undergoing compression and refraction. Now, the pressure in the insinuated tissue increases and decreases rhythmically As such, just the same way the transducer crystal expands and contracts. Now, positive pressure peaks are associated with compression, and negative pressure peaks are associated with rarefaction. Pressure can be measured as wave amplitude. Now, the greater the force applied and the smaller the area it is applied to, the greater pressure that will be exerted. The pressure is proportional to the magnitude of the transducer excitation voltage, which is usually governed by the output power control. Increasing the frequency or the amplitude of the excitation voltage at the transducer increases the acoustic pressure. That's to say, it also increases the output power and beam intensity with increasing risk of hazardous biological effect. Beam width also affects pressure. So pressure and intensity are inversely proportional to area. Now, the smaller the beam width, the greater the pressure and intensity. All the factors which influences beam width will also affect pressure and intensity. For example, a focused beam will produce highest intensity between the transducer face and the focal point. Focal point is actually the narrowest beam diameter. Power as a quantity. We know that power is the rate at which the ultrasound energy is emitted, or rather, the ultrasound energy is emitted from the transducer. Now, it is energy per unit time, and the unit, of course, is measured in watts or milliwatts. So 1 watt is equal to 1,000 milliwatts. A milliwatt is like a 1/100th of a watt, right? Now, the acoustic power emitted by diagnostic ultrasound is typically in a low milliwatt range, about 20 to 100 milliwatts. Pulse Doppler produce more power in range of 2,000 milliwatts. Now, this is considerably high than the grayscale imaging ultrasound. Now, power is proportional to amplitude of the wave squared. Having known that, look at the third quantity, intensity. Intensity is power divided by the beam area, and the unit for that is watt over centimeter square or milliwatt over centimeter square. Beam intensity depends on the output power level and beam profile. So the more focused the beam is, the more intense the beam is. Yeah. Now, intensity is directly proportional to power and inversely proportional to beam area. So the highest the beam intensity exists, the highest beam intensity exists in the focal zone. The higher intensity generates stronger echo, which improves system sensibility. And of course, intensity in the equation is power measured in milliwatts divided by beam area centimeter square. However, the possibility of biological effect is also increased with higher intensity. The intensity of the diagnostic ultrasound beam is difficult to measure because it varies considerably within the beam. The beam profile is an hourglass shape because sound converge to diverge. So after the focal point, there is divergence. So how do you measure across these various beam width? And in the case of pulse transducer, within time, there is the on time and the off time. So on time is when the pulse is on, and off time is when the pulse is actually off. So for this reason, ultrasound beam intensity can be described in terms of both a spatial intensity and temporal intensity. Let's look at them one after the other. Spatial intensity, for example, is referred to the measurement of ultrasound intensity at a specific location within the beam. There are two spatial factors for intensity for both the pulse wave and continuous wave transducer. The first is the spatial peak intensity, which is SP, and the second is the spatial average intensity, which is SA. So where are these spatial intensities measured in the sound beam anyway? Spatial peak intensity, SP, is the maximum intensity in the sound beam and is measured in the center in the focal zone. Yeah. Now, SP intensities for focus transducer are higher than for unfocused transducer, because focused transducers have smaller beam width, smaller beam area. Now, spatial average intensity is the spatial intensity average over the entire area. It is typically measured at the face of the transducer. For a focused transducer, the spatial average intensity SA is always lower than the SP, because at the face of the transducer, beam is larger than the focal zone. Now, temporal intensity, the pulse ultrasound beam intensity varies with time, because a pulse transducer alternates between transmitting, that is the on time when it's transmitting, and the receiving, the off time when it's receiving. Now, there are three parameters describing the temporal variation in beam intensity. There is the temporal peak, TP, there's a temporal average, TA, and there's a pulse average. TP intensity is the highest temporal intensity. It is the instantaneous peak temporal intensity during the pulse duration, PD, when pulse is actually on. Now, TA intensity is the temporal intensity average over both the pulse duration, that is the on time, and the receiving time, the off time. Now, since the system remains off for much longer time than it's on during each cycle, the TA, temporal average intensity, is relatively low, because TA intensity is related to the TP intensity by duty factor, and the equation for that is TA intensity is equals to TP intensity times duty factor. PA intensity is the average value during the pulse duration. It is the average intensity while system is being transmitted. Now, this is low than the TP, but higher than TA. Now, the factor that relates the PA and TP intensity is called the duty factor. And duty factor is that fraction of time that the sound is actually being transmitted compared to the total time. Duty factor is unitless, and a typical duty factor in pulse ultrasound is about 0.0001, meaning that the sound is actually only on for only about 1/100th of the time. Whereas that in continuous wave ultrasound, the duty factor is 1, meaning that the sound is on for the whole cycle of time. So how do we calculate the duty factor? The duty factor of ultrasound equipment can be found by dividing the pulse duration by the pulse repetition period, PRP. Now, typical duty factor in a pulse ultrasound is 0.001 to 0.0001. and must be less than 1, basically, because it's not always on. Whereas duty factor for continuous wave ultrasound is 1. Okay, let's talk about ultrasound dose or acoustic exposure. You see, acoustic exposure is the ultrasound dose the patient receives during an examination period. The ultrasound dose basically relates to the amount of ultrasound energy in the sound beam and the duration of exposure. Ultrasound dose depend on intensity, power, and time. It can be calculated as a product of intensity and time. That means ultrasound exposure can be reduced by reducing intensity, power, and or time. Now that brings us to the ALARA principle. ALARA principle, or rather ALARA, means as low as reasonably achievable. It is the principle that guides the use of all energy used for diagnostic imaging, including both ionizing and non-ionizing modalities. So applying the ALARA principle simply means that the patient exposure to radiation energy should be kept as low as possible. Understanding how to reduce the patient exposure to energy is very important if you want to apply the ALARA principle. For example, if good image can be obtained in an average patient using only 50% power, then power should be reduced appropriately. If more power is needed to produce a diagnostic image in a large patient, then the power should be increased. Only do that when it's necessary. In diagnostic ultrasound, ALARA principle is implemented by the following practice. 1. Use diagnostic ultrasound only for valid medical reasons. Number 2. Do not do ultrasound without valid indication. So, especially for entertainment purposes. For example, you just want to take baby face with 3D or 4D. Number 3. Use Doppler prudently and effectively. Number 4. Use low power. So, if you use low power, you can learn how to increase and reduce your gain whenever possible. Because if you use that effectively, your power will remain optimized. Number 5. Minimize exposure time. And to minimize the exposure time, you have to perform exam as efficiently as possible. You please minimize minimize repeat scans where necessary. You only send for repeats, but if it's not necessary, you don't have to. The next is maintain equipment in a good operating condition with effective quality control program. Now, this list of control can be used to reduce exposure and help apply the ALARA principle. So look at the parameters affecting acoustic pressure. The power, for example, the control will be the output control, and increased power will mean increased exposure, and that means increased effect. Spatial intensity, you can achieve that with the control button and focusing. And increased power, increased intensity means increased exposure. Increased focus means increased intensity, and that will be increased exposure. Then temporal intensity, the control is the depths, PRF, that's what it was. So increased PRF will mean increased TA intensity and increased exposure. Examination time is one of those parameters. So you have the on and off switch. So increased examination time means increased exposure. So how can acoustic exposure to the patient be minimized during the course of an exam? The most effective methods are 1. to minimize the examination time as much as possible. Number two, keep it at the minimum level required to obtain the necessary diagnostic information. Increasing the receiver gain will help keep power as low as possible. Now, we may need to take necessary time to obtain the diagnostic information, but we must perform the exam only when required and as prudent as possible. A good quality assurance and control program will also help to reduce patient exposure by minimizing the number of repeat exams that are required as the equipment, as a result of equipment malfunction. So, acoustic output labeling standard. Prior to 1992, the maximum output that could be generated by an ultrasound system was largely governed by the limits set by the FDA in the United States. For example, a cardiac system was limited to maximum SPTA intensity of about 430 milliwatts per centimeter square, and the obstetric system had a limit of 94 milliwatt per centimeter square. However, with the increasing use of Doppler, it was felt that the FDA limits were too restrictive. Therefore, in 1992, the AIUM and NEMA adopted a voluntary standard for display of acoustic output information known as the ODS. And ODS is the Output Display Standards, in order to better the implementation of the ALARA principle and give the sonographer more control over the acoustic output. So the ODS consists of two indices. They are displayed on the viewing monitor and provide real-time information to the sonographer about the potential effect, biological effect. There are two indices here. You have the thermal index and the mechanical index. So both are unitless. Both are real. They are actually relative values. So the range for both is approximately 0.2. So a value less than 1 indicates very low potential for bioeffect. A greater than 1 indicates an increased potential for bioeffect. Now, this should prompt the operator to ensure that the ALARA principle is applied. So let's look at them one after the other, starting with thermal index. Thermal index is a relative index of temperature rise. The thermal index gives an indication of the potential for increasing tissue temperature. A high index means that the potential for thermal biological effect exists. So the TI, that is thermal index, is equal to the transducer's acoustic output power divided by the estimated power that is required to raise the tissue temperature by 1 degree. 3 indices are used because the different media have different potential for thermal effect. For example, the acoustic power needed to cause a temperature rise of 1 degree in bone is much less than in soft tissue, because the absorption of sound by bone is much higher than by soft tissue. So the indices are TIS, which is thermal index for soft tissue, TIC, which is thermal index for transcranial Doppler, and TIB, which is thermal index for fetal bone when you are doing obstetrics at 2nd trimester and 3rd trimester. It is important to know that a TI value more than one indicates an increased potential for thermal biological effect and should prompt the operator to ensure the ALARA principle is being practiced. So what should you do if the TI exceeds a value of 1? Okay, the first thing to do, ensure appropriate index is being used. So which index do we have? The TIS, the TIC, and TIB. For most applications, it should be the TIS because mostly we deal with soft tissues. 2. Look for ways to reduce the TI without compromising the image quality. Optimize the scanner control. That's what they are there for. Where possible, try to reduce the power, then increase your gain. To manipulate your buttons to see the best optimization you can get on your exam. Number 3, look for ways to minimize exposure time without compromising diagnostic quality. The maximum exposure duration should be calculated using this formula, 4 to the power of 6 minus TI in minutes. So, however, the exceeding exposure limit would be very unlikely in clinical practice. It's very unlikely to exceed the exposure limit. The reason why we say ultrasound practice has shown no effect so far. Now, mechanical index is used to estimate acoustic outputs that have the potential for mechanical bioeffect called bubble formation or cavitations. A mechanical index that is greater than 1 does not indicate bioeffect. It rather describes that the potential for cavitation bioeffect has increased. The potential has increased, not that the cavitation is being is happening. The operator should ensure that the ALARA principle is being applied when you see this value. Look for ways to reduce potential exposure to exposure that will not compromise the diagnosis. I want to thank you sincerely for joining this lecture, and I'm sure we've learned something very valuable. So we'll see in the next, in the part 2 of Bioeffect, where we'll discuss more detailed information. But please, I want you to like, share, subscribe, and put on the notification to receive all our free lectures. For more information about our paid classes, please send an email to sonoeyesdiagnostics@gmail.com, or you can WhatsApp me at +234 9019 144 175, or you can visit our online store at sonoeyes.business.site. Attempt the quiz in the description and leave me a comment. Until the next time I come your way again, keep learning ultrasound.